Okay, good afternoon. Just going back to what we have in the case of functions, and we have regarding average rate of change of a function. And again, this what we have with average rate of change of a function. This is going to be in reference to like a formalized version of what we have in the slope. And just for average rate of change of a function, we have as a bit of a backdrop. And we have from page 163, okay, we have like a graph. Okay, we have a curve that consists of a straight line that's going through two specified points. And those two specified points we have 1, 6 as well as 5, 2. And I'll get into the graph in just a moment, but for the average rate of change of a function, y is equal to f of x. Just for the setup, for average rate of change, okay, going from one point where we have x1, y1 is equal to x of 1, f of x of 1. Again, f of x of 1, this is going to be a functional notation for what we have for y of 1. And we have for the other point through which we're going to have involving the average rate of change of a function. Okay, we have x of 2, y of 2, where we have y of 2 at f of x of 2. And for what we have regarding the average rate of change of a function, now a line that's going to go through 2 points on the graph of a function, this is going to be referred to as the secant or the secant line. And the average rate of change, okay, you still have preserving the concept of slope, and you had the slope m is equal to it had this SEC subscript, which will be in reference to the secant line. So you had the slope of the secant line. And again, we have y of 2 minus y of 1 all over x of 2 minus x of 1. And the functional notation translation for this, we have f of x of 2 minus f of x of 1 all over x of 2 minus x of 1, whereupon x of 1 and x of 2 are not equal to each other. And just looking at what we have in reference to the graph. So you have 1, 6. If we let this be the first point, again, just in xy notation, we can say this is x of 1, y of 1. And in the functional notation, we have x of 1. And in lieu of y of 1, we have f of x of 1. For the second point, we have 5, 2. So we have x of 2, y of 2. And in functional terms, we have x of 2. And again, replacing y of 2, we have f of x of 2. So for the average rate of change of the graph I have in blue, okay, going from 1, 6 to 5, 2. Okay, again, that's going to be the slope of this particular secant line. And just filling in, so we have for f of x of 2 minus f of x of 1. Okay, this is spelled out as 2 minus 6. And for x of 2 minus x of 1, okay, we have 5 minus 1. And so you have the vertical change will be minus 4 units. And the horizontal change, we're going to have 4 units. And so we have in the ratio, we have negative 4 over 4. And so that is going to be equal to negative 1. Okay, so now for this particular curve, now the slope can be changing continuously. It might be positive one moment and then negative the next. And for 2 points of interest, okay, for the activity between 1, 6 and 5, 2, it just happens to be that for the slope of that immediate, within that immediate framework, that we have the average rate of change to be the slope of negative 1. And so for nonlinear functions especially, now the average rate can change continuously. And just sort of drawing up a case here, and we can say that if we have and we say we have given a function, okay, so we can say that y is equal to f of x is equal to x squared plus 2x. So you have this particular function that is given. So you have y is equal to f of x is equal to x squared plus 2x. And let's say that from this function, if you're looking at determining the average rate of change, say we have between x equals 1 and x is equal to 5, and also between x equals 1 and x is equal to 9. So in both of these cases, right, we have the initial point, okay, starting out at x is equal to 1. And what we can do is that, now remember, f of x is a functional notation for what we otherwise say is y. And just sort of laying the groundwork. Okay, so I have f of x is equal to x squared plus 2x. And if I start out, okay, say from x is equal to 1, so we have x is equal to 1. Okay, so we're going to have that y is equal to f of 1 and we have is equal to 1 squared plus 2 times 1. So we have that 1 plus 2 is equal to 3. So you're looking at a point on the graph of y equals f of x equals x squared plus 2x, okay, to include 1, 3. So when x is 1, y is 3. So 1, 3 is a point on the graph of this function. Now we have with x is equal to 5, okay, so for x is equal to 5, so we have 5 squared plus 2 times 5. So yeah, 5 squared is 25, 2 times 5 is 10. 25 plus 10 is going to make 35. So another point on the graph of this function, okay, we're going to have at 5, 35. And we can go ahead and determine the y value whenever x is equal to 9. And for the corresponding y value, okay, so you have f of 9 okay, so you have just like running through the same treatment as we did earlier with x at 1 and x at 5. Okay, now we're going to have the square of 9, which is going to be 81. 2 times 9 is 18. And the sum of 81 and 18, okay, we have at 99. Okay, so we have with the ordered pair, okay, we have at 9, 99. Now for the average rate of change, I'm going back to part A here. So between x equals 1 and x equals 5. So you're looking at the average rate of change between, in ordered pair terms. So you're looking at going between 1, 3 and 5, 35. So we have with the average rate of change. Okay, so you have the slope of the secant. Again, just for the formalized notation, so you have, again, so you have f of x of 2 minus f of x of 1 all over x of 2 minus x of 1. So we have, again, so for the change in x, okay, so you have x of 2 minus x of 1, we can say we have 5 minus 1. And again, for f of x of 2, this is your f of 5, which is going to be 35, minus your f of x of 1, which in this case is going to be f of 1, which we have at 3. So the change in y is going to be 32 units. And again, the shift in x is going to be 4 units. So the average rate of change in this case is going to be 8. Again, that is for the activity between 1,3 and 5,35. And again, as we venture out further along the x-axis, so we have between x equals 1 and x is equal to 9. So again, I'm going for 1,3 and venturing out to this time 999. So we have here, okay, so for the average rate of change, okay, so going from 1,3 to 999 for the change in y. So this time we're going to have 99 minus 3. And for the change in x, I have 9 minus 1. Here we have 99 minus 3. It's going to be at 96. 9 minus 1 is 8. And so going from 1,3 to 999, it's going to turn out that the average rate of change between these points is going to be 12 units. And so just kind of taking what we have let's see. Here's a little part here I put up earlier. There we go. Okay, so for the activity we have going on, okay, so for this particular curve, okay, this is a section of what we have, okay, regarding what we have concerning the function. Okay, so you have f of x is equal to x squared plus 2x. And in the case of what we have with the secant lines, so let me readjust this one here. There we go. Okay, so we have for the activity, okay, for the slope of the secant lines. See if I connect 1,3 and 5,35. Okay, So between x equals 1 and x equals 5, we're going to have the average rate of change. In this case, you had the slope of that particular secant line is going to be at 8. And as we once again go out and proceed, let's say out to x is equal to 9, and starting out from x is equal to 1. So we have just see if I can connect those dots. Okay, so we have in the case of the slope of the secant line out here, okay, that turns out to be 12. Okay, so for this function, the average rate of change, okay, you have just varying continuously. And for the behavior here, as you go out farther in the x-axis out to the right, okay, so the curve becomes steeper and the slope is going to be changing. And so we have, in effect, the average rate of change is going to be continuously increasing. And if you go out to very high values in x, it'll look as if the average rate of change is going to be approaching infinity. All right, so this is what we mean by average rate of change. Okay, and in this one, for this nonlinear function, you have, again, you have continuous change throughout. And so let me create a little bit of room here. And just crossing over to what we have for not just individual functions, but also interaction between functions. And for this next particular part, you probably saw this at the bottom of the screen earlier. And we have what we regarded as operations between functions. And we'll say that we have for two given functions, f of x and g of x. Okay, now we'll be looking into, let's say, just the first 4 operations, and there will be other operations included, but for the common ones, okay, so you have for what's referred to as the sum function. And now the shorthand notation for the sum function, okay, we have f plus g of x. And this will translate out to f of x plus g of x. And the expansion is going to be displaying the functions in the order that you see them in the compact notation. Like if I had g plus f of x, this will come out to g of x plus f of x. Now for the difference function, we have f minus g of x. And so that becomes f of x minus g of x. And for the product function for f times g of x, so we're looking at f of x times g of x. As for the quotient function, we have f over g of x, and that is going to be equal to f of x all over g of x. And again, when we looked at functions, okay, we had also looked into domain, okay, and now for the operations between functions. Now the sum, difference, and product functions, all of these are going to have the exact same domain. Okay, so they're going to have the exact same domain, okay, and the domain is going to be, okay, formed by combining the restrictions, if any, of f of x and g of x. Regardless, okay, the sum, difference, and product functions are always going to have the exact same domain. Okay. Now for the quotient function, because it's imposed that whatever we have for g of x, that the bottom part of a fraction cannot be zero. There's still that possibility that while the sum, difference, and product functions will have the same domain throughout, it might be that the quotient function might have the same domain, but because that we had that g of x cannot be equal to 0, the quotient function can have a different domain. And just kind of taking as an example for what we have for operations between functions. See, if I were to determine the sum, difference, product, and quotient functions. As well as their domain. And we'll say that we have given, okay, we'll say that for f of x, we'll say that we have given as let's say we have 3x plus 4 and g of x is equal to x minus 7. Okay, so if we're looking at the sum, difference, product, quotient functions, as well as their domain, I'm just using the algorithms, okay, as kind of a backdrop. Okay, so we have with f plus g of x, we have f of x plus g of x, and then specifying, okay, so f of x, we have at 3x plus 4, And g of x, we have x minus 7. And if I add f of x and g of x, so again, we have 3x plus 4 plus x minus 7, and combining the terms together, we have 3x plus x becomes 4x, and 4 minus 7 becomes negative 3. So for the sum of the functions, this will come out to the difference statement, 4x minus 3. So if you add functions together, your result might be something other than addition, like in the case of this instance. Now, for the difference of functions, for f of x minus g of x, so from f of x, I have 3x plus 4. I got subtracting. Now g of x, again, we have x minus 7. So again, we still have f of x at 3x plus 4. And subtracting g of x. Now both x and negative 7 will be affected. So x will become subtracted. And what was minus 7 is going to translate to the addition of 7. And we have with the output, we have 3x minus x is 2x. 4 and 7 will make 11. So the difference function translates to 2x plus 11. And for what we have in the case of the product function, so f of x, we have 3x plus 4. And we have times g of x, which we have at x minus 7. And if I multiply together, so you have 3x times x, so this will be 3x squared. Outside product is going to become negative 21x. Inside product we have at 4x. And the last product, okay, we're going to have at negative 28. And I'll just move this on down. So I have middle terms to combine. So I have 3x squared minus 17x minus 28 for the result. And for what we have in the case of the quotient function, we have f of x. Okay, so we have at 3x plus 4. And g of x, we have at x minus 7. And there's no common factor other than 1, okay, shared between the numerator and denominator. So just filling in for f of x and g of x, respectively, with 3x plus 4 and x minus 7. That will be the end result here. Now, for what we have in the case of the domains, okay, so with f of x equal to 3x plus 4 and g of x equal to x minus 7, okay, we have both of these are linear functions, and we do not have any even root radicals, nor do we have any fractions involved. So x for both of these can be anything 0, positive, or negative. So f of x has no restrictions. And so at least for f of x, now that part, okay, now the domain will be the set of all real numbers. And the same thing is going to apply for g of x. Okay, so we have no restrictions. Again, x can be anything from the real number system, so we have the domain for that to be also the set of all real numbers. And guess what? Since there are no restrictions for f of x or g of x, we can have anything for f of x and g of x, whether it's negative, 0, or positive, throughout the sum, difference, and product functions. So we have everything from before is going to sort of cascade through for the first 3 operations, but we have the set of all real numbers throughout for the domains. But once again, it is with the quotient function that this could be the unique individual in terms of having its own domain. Now for the quotient function, notice you have 3x plus 4 over x minus 7. And again, for a quotient function to be defined, or in this case a fraction to be defined, the bottom part cannot be 0. So we have the x minus 7 cannot be 0 in value. And so we have in consequence x cannot be at 7. And so it's going to turn out that for the domain that we have for the quotient function, instead of all real numbers, okay, we have almost all real numbers, but we're going to have 7 excluded. So the domain is going to be the set of values x, which will be less than 7, in union with the set of values of x such that x is greater than 7. Okay, so we have, in the interval notation, we had the formation of 2 subintervals. All right, and tell you what, just for the next few moments, okay, tell you what, let's see what we get for the sum, difference, product, and quotient function results, as well as domain. And we'll say that we have given let's say that we have f of x is equal to x squared plus 3, and we'll say that we have g of x is equal to x squared minus 4. Okay, just looking at what we have for the operations between functions. Again, we have f of x is equal to x squared plus 3, and g of x we have equal to x squared minus 4. Okay, so looking at the sum of the functions, okay, so we have, again, so we have f plus g of x, we have f of x plus g of x. So f of x, okay, again, we have with x squared plus 3. And g of x, okay, we have with x squared minus 4. And so looking at adding f of x and g of x, so we have x squared plus 3 plus x squared minus 4. So combining like terms together, okay, we have x squared plus x squared will make 2x squared. And 3 minus 4, this will become negative 1. So for the sum of these functions, okay, we have 2x squared minus 1. Now, for what we have in the case of the difference between the functions, so we have x squared plus 3 minus all of x squared minus 4. Now looking at distributing the subtraction, okay, so we have in the rewrite, so we have x squared plus 3, and we have minus x squared. Subtraction negative 4 reverts to addition of 4. And for the difference of these functions, okay, we're going to end up with a constant. Now x squared and negative x squared will cancel out, and we have 3 plus 4 is equal to 7. Now in the case of what we have with the product function, so for f of x times g of x, so we have the quantity of x squared plus 3 times that of x squared minus 4, and multiplying together. Okay, so we have x to the 4th, and we're going to have minus 4x squared plus 3x squared. and we have plus 3x squared minus 12. And so looking at combining like terms in the middle, so we have for this output, we're going to have x to the fourth minus x squared minus 12. And for what we have in the case of the quotient function, okay, so again, we have f over g of x, which we have f of x over g of x. So we're going to have x squared plus 3 all over x squared minus 4. And there's no common factor that will cancel between the numerator and denominator. But you could write the quotient function, you can either leave it as it is, but if you were to express in factored form, well, with x squared minus 4, that will go to the quantity of x plus 2 times that of x minus 2. Okay, and now where the domain is concerned, okay, now there's going to be a bit of history to repeat. You have f of x equal to x squared plus 3, so you don't have a fraction, you don't have an even root radical, so x could still be a negative, a 0, or a positive. Same thing for the x in g of x. So we have no restrictions. And so that means that for the domain of both of these, okay, we're going to have the set of all real numbers. And again, that's going to carry over to the sum, difference, and product functions. Okay, so for the sum, difference, and product functions, okay, we still have the domain as the set of all real numbers. And looks like for what we have in the case of the quotient function, again, it's going to have still once again a domain that is different. Okay, so again, we had that the denominator cannot be equal to 0. And if x squared minus 4 cannot be 0, well, neither can the factors. And so for what we have here, if x plus 2 cannot be 0, then we have that x cannot be equal to negative 2. And if x minus 2 cannot be 0 in value, then we have the x cannot be at 2. All right, so I'm just looking at what we have excluded, okay, from the domain of the quotient function. Again, we have negative 2 and 2 are going to be left out. So we have holes at negative and positive 2. And also you have in the activity case, you have those values of x less than negative 2, those between negative and positive 2, but not including negative or positive 2. And then we'll have those values, okay, that will be greater than 2. Okay, and so we have with the limits. it's going to turn out that, okay, for the domain of the quotient function, okay, so we have those values of x less than -2, so in interval notation terms, okay, we have parentheses, okay, around -infinity and -2. Then for the next build up, okay, we have parentheses around negative and +2. And then we have for the final stretch, you'll have parentheses around 2 and infinity. And again, this will be the domain of what we have with the quotient function. Now, so far we've been looking at functions only in the general domain. Let's say that if we're looking at operations for specified values, or operations for specified input values. Now let's say that if we have functions given, in fact, I'll say that I have, let's say given f of x is equal to x squared plus 5. G of x is equal to 2x minus 7. And we'll throw in h of x is equal to x plus 10. And we're looking at determining, let's say, we have f plus g of 2. And we'll say we have f minus h of 7. And then we'll say that we have we'll say we have h times g of 4. And we'll say we have h over f of 9. Okay. So for the specified input values, okay, so you have 2, 7, 4, and 9. Now, just looking at taking what we have, we have for f plus g of 2. Now, one way that you can go about this is that we can say that for f plus g of 2, just like f plus g of x goes to f of x plus g of x, we're now going to have f of 2 plus g of 2. And upon looking at the determination of f of 2 and g of 2, so we have for f of 2, okay, so we have with x at 2, so we're going to have 2 squared plus 5. 2 squared is 4, 4 plus 5 is 9. And since we're working with g of 2, okay, so g of x, you have 2x minus 7. So for g of 2, we have 2 times 2 minus 7. 2 times 2 is 4. 4 minus 7 becomes negative 3. So we have in following through, so we have with f of 2 plus g of 2. So f of 2, okay, we have at 9. And plus g of 2. Now g of 2 we have at negative 3. And guess what? 9 plus negative 3 is going to be 9 minus 3. And so we have for that output, this will end up at 6. Now for the next scenario. Okay, so for f minus h of 7, okay, so we have an expanded notation. So this would be f of 7 minus h of 7 okay, so we're working with the f function once again. So f of 7, so we have 7 squared plus 5. 7 squared is 49. 49 plus 5 becomes 54. Now for h of 7, again, you have h of 7, so this would be 7 plus 10. And 7 plus 10 is 17. So we have in the follow through. Okay, so f of 7, we have at 54. We have minus h of 7. Again, h of 7, we have at 17. So for f minus h of 7, okay, this will reduce to 37. Now in the case of h times g of 4, and so this is going to translate out to h of 4 times g of 4. Okay, so we have, now again, h of x we have stored as x plus 10. So for h of 4, so this is going to be 4 plus 10, which you have at 14. And for g of 4, again, the g of x is 2x minus 7, so we have 2 times 4 minus 7. 2 times 4 is 8. 8 minus 7 is 1. And so this will become 14 times 1. And so we're going to have for h times g of 4, this is going to be 14. And for h over f of 9, okay, so this will become h of 9 over f of 9. Okay, so for h of 9, okay, so for h of 9, okay, so we have 9 plus 10, which will be 19, okay, and we have for f of 9, okay, so again, you have x squared plus 5, so in this case you have 9 squared plus 5. 9 squared is 81, 81 plus 5 is 86. And so we have for this output, okay, so just directly, okay, h of 9 we have at 19. F of 9 we have at 86. So you have 19 over 86. And those will be your outcomes. Now, just one other thing. Okay, now just going back to domain and the general case. And let's say that if you have a situation where you're not going to have so much of the set of all real numbers for the domain, especially with the first three operations. And let's say that if we have not looking for the operations this time around, but just determining the domain. Okay, so we have, we start out with f of x. We'll say is equal to 3 over x plus 4. And we have g of x, and we'll say that we have is equal to let's see, have x minus 4 over x plus 1. And then we have with the sum difference in product functions as well as the quotient functions. Okay, now if we place the restrictions, okay, just for what we have at the start. Okay, so we have with f of x equal to 3 over x plus 4. Okay, for f of x to be defined, x plus 4 cannot be 0, so that means that x cannot be negative 4. Now for g of x, we have x minus 4 over x plus 1. So here we have a couple of x expressions. But again, because g of x is a fraction, okay, the restriction is going to come with the denominator section. So in this case, x plus 1 cannot be 0. So that means that for g of x to be defined, x cannot be negative 1. All right. And just carrying over what we have here. Now for the sum, difference, product, and quotient functions. Again, I'm working with f of x, and to be able to work with f of x, x cannot be negative 4. And because all four of these operations are also working with g of x, guess what? To be able to operate with g of x, we must keep g of x as a defined value in the real number system. So we have also that x cannot be negative 1. Okay, again, x cannot be negative 4 in order to be able to work with f of x. And also x cannot be negative 1 in order to be able to work with g of x. Now, for the domains. Okay, so for f of x, we have only negative 4 excluded. Now for g of x, okay, we have only -1 excluded. Okay. Now again, for the sum difference and product functions, all of these will have the same domain, which will be formed by just combining the exclusions from f of x and g of x. So this time we're denoting that both -4 and -1 are left out. So again, the sum difference and product functions will consist of the same domain. Okay. Now, in the case of the quotient function, we're still going to have -4 and -1 left out, but there can still be a different domain throughout. Okay. And again, just for f over g of x, to see if there's any key detail that has not been presented in terms of any possible restrictions. Okay, so you have f of x over g of x. Again, with f of x, again, we had 3 over x plus 4. And we have with g of x, again, this was x minus 4 all over x plus 1. So again, f of x is a fraction, cannot have a 0 denominator, so x cannot be -4. G of x also a fraction, and for this fraction, x plus 1 cannot be 0, so x cannot be -1. Now if you notice in the layout, we have a ratio where you have a fraction over a fraction. And what I can do here is that if I rewrite what I have here, and thus be able to condense or simplify. So I have 3 over x plus 4. As for x minus 4 over x plus 1, there's a rule of thumb that if I divide by a fraction, it'll be the same as multiplying by that fraction's reciprocal. So I'm now going to have 3 over x plus 4 times, and then flipping the bottom fraction, and we have times x plus 1 all over x minus 4. And so we have for the end result here, okay, we have 3 times the quantity of x plus 1, and this will be all over the product of x plus 4 times x minus 4. And guess what? Now, originally we had x plus 4 and x plus 1 in bottom positions. And now, you notice we have x minus 4. We have an added restriction, because now that this fraction is flipped on its end, we now have x minus 4 on the bottom. So we now have that x minus 4 also cannot be 0 in value. Okay, so we're going to form a trio of exclusions in order to keep the quotient function defined. And so we have for the resulting domain for the quotient function, so you have going from -infinity approaching the smallest of the exclusions. So you have -4 in parenthesis, and then we have bypassing -4 approaching the next smallest value, so you have approaching -1. And this time we have bypassing -1 not approaching infinity, but this time this third exclusion, which you have at 4. And 4 is bypassed, and for the rest of the domain in interval notation, so you have the set of values x, which will be greater than 4, And once again, we have parentheses throughout. And the more exclusions there are from the domain, the more subintervals there will be formed. So you got one exclusion, two subintervals, two exclusions, three subintervals, and now with three exclusions you have like yet another subinterval added.